You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Klaus Pontoppidan. Dr. Pontoppidan is an astronomer at the Space Telescope Science Institute. He works on the formation of planets and the origin of our own solar system. He also works as a James Webb Space Telescope project scientist. The James Webb Space Telescope is the scientific successor to the Hubble Space Telescope and the Spitzer Space Telescope. As the largest optical infrared telescope ever launched into space, it is expected to spot the most distant galaxies in the universe, dust, and molecular gas around young stars in the process of making their own planetary systems, and not least, to characterize the atmospheres of exoplanets.
Dr. Klaus Pontoppidan, welcome back to the program.
Thank you so much.
Klaus, watching that launch of JWST on top of an Ariane 5 rocket, even though it was cloudy, it was probably one of the most amazing sights I've seen in 35 years of being a space enthusiast, just because it was such good news and such a perfect launch, which, as we all know, the world needed some good news, and JWST has delivered that. Now, how good was the launch within, the design parameters?
Yeah, it was an amazing launch. And just also, as you say, given the stakes, just watching that, my hands were shaking, and I was looking around the room. I was here in the Mission Operations Center, and it was amazing. We showed it on loads of screens. The Ariane 5 rocket, which was supplied by the European Space Agency and Arianespace, performed marvelously. It was really good. And so what that means is that we didn't have to use as much fuel for the course corrections on the way to L2, which means there's more fuel available for science operations. So that was just great news.
Now, as you go through the science operations, are there other opportunities for conserving fuel? I mean, is it possible from this point on now to conserve even more and extend the telescope's life well beyond 10 years?
And that's something that certainly we'll work on. So the amount of fuel that is needed is linked to exactly which astronomical targets we're observing and in what order, because some of the fuel is spent making sure that the observatory can point in the right direction. What happens is you have this big sun shield, and the solar radiation, the light from the sun pushes on it, and it's just like a solar sail. So if it has some angle to the solar light, it starts to turn, and you have reaction wheels on the spacecraft that take up that angular momentum. But at some point, they're just full. They can't turn any faster. And so you have to do a rocket burn to spin them back down again. And so you can imagine, like anybody who is familiar with sailboats, exactly, how much time you spend at this angle, how much time you spend at that angle will impact on how much of this angular momentum you pick up from the solar radiation. And so that depends on how efficiently we can schedule the observations. And it's something we worked on for a while, but it always depends on what the scientists around the world actually want to look at. And so in the first few years of science operations, I'm sure we'll try and optimize that.
Now, how far out are we to actual science? I mean, by the end of this year, will we be making measurements?
Oh, yeah. So we're in the commissioning period now, which is, as we've seen, the major deployments. It's cooling down the telescope. It's aligning the mirror itself and focusing it, and it's checking out the instruments, making sure that they function the way they need to. And that whole process takes 6 months. And so everything is going really well right now. So what we're looking at is we'll do the first science observation sometime this summer.
So not that far away. Now, we sort of have breaking news because earlier today, the port side mirror assembly deployed successfully. And this means, and we had this before actually, as soon as the secondary went up, there's a telescope in space. And if, heaven forbid something were to happen, is the telescope usable in this form?
Yes, it is. It is. So the really big deployments that we were so worried about, I mean, of course, we're worried about all deployments and they're all critical, but unfolding the sun shield to make sure that the telescope itself and the instruments are cold. If that hadn't unfolded, we wouldn't have a mission. And putting down the secondary mirror, which was already done, that is also required in order to have a telescope. The wings are important, but we still have a telescope without a wing. We just have, instead of having 18 segments, we have 15. Images of stars might look a little wonky, but there's still things that could be done. But of course, we're confident that things will go well tomorrow when the last major deployment is done.
Now, what happens after this next wing deployment? What's the process for the rest of the month until the final burn?
Right. So we still have a couple of weeks until we reach the L2 orbit. So that happens at day 29. In between there's still a lot of cooling that has to be done on the telescope. It's now cooling down after it's been shielded by the sun shield, but this doesn't happen instantaneously. It takes several months actually for everything to cool down to their operating temperature. And then we have to align and phase, it's called focus, the telescope itself. And as it's unfolded in space, each segment right now kind of functions as its own independent telescope and a very unfocused telescope at that. Right? So we have probably light that is hitting the primary mirror and reflected into the instruments at this time, but it's not usable for anything. It's completely out of focus. And so that process of aligning all the segments and focusing them so they function as a single large 21-foot primary mirror is a fairly long and arduous process. 1 or 2 months it will take to actually do that. And then once that is done, then we still have to check out all the instruments, the four science instruments, all their complex observing modes, not just imaging but spectroscopy as well. Our ability to take spectra of exoplanets, for example, all these things have to be calibrated and measured, and so we can ensure that they function the way they're supposed to, and that they give us the quality of science data that we need to do the science. And so that's why we're looking at this 6-month long period that is really necessary before we can do the science.
Now, having built a telescope or two in my lifetime, this is optics that we're talking about. So precision is of the utmost importance, especially getting that wave of that mirror all together. But it's sort of a risk-free or less risk than the actual deployments, right? So the actual adjustments, you've got some leeway there, right? As far as being able to get them aligned.
Yeah, so each segment has 6 actuators that sit behind it. You can push on it and change its shape. So you're right; that gives us a lot of parameters that can be tweaked so that we can ensure that the telescope is as sharp as it needs to be. And even during science operations, we expect to tweak this focus every so often.
Now, when you do that, tweaking the focus, how long does it take to actually position a mirror? Is this a very, very, very slow process, or can it actually be done within a day?
So once everything is focused during commissioning here, once you've been through this long period, then tweaking it is not something that's going to take weeks or months anymore. That can be done relatively quickly. And hopefully not too often. So we do think that we have the great majority of time during science operations to actually do science and not spend it all on calibrations and this kind of activity that isn't yielding science data in itself. So we think we'll be quite effective.
Now, the science data characterizing exoplanet atmospheres. Do we have any candidates to start with?
Oh yeah. There's quite a number of exoplanets that are already on the schedule for the first year as part of the regular science program. I think it's more than 60. Maybe the most famous one is the Traapist-1 system, which consists of 7 planets with rocky surfaces. 3 of them are in the Goldilocks zone, and these are, of course, prime targets. Everybody's waiting to see what we find out about them. My biggest question is, and this is really a yes/no question that will come out pretty quickly, is whether these planets have atmospheres even or not. So we don't know that yet. Obviously, if you're looking for potentially habitable planets, and they're not going to be habitable in the way that we know it if they don't have an atmosphere, even if they're at the right temperature. So that's definitely one of the first questions we'll try to answer.
Now, is there any way to infer from atmospheric data on an exoplanet whether or not it has, say, oceans of liquid water that you can't really directly detect?
At some level, yes. Now, I can't predict necessarily all the clever ways that exoplaneteers will figure out how to use this telescope and how to use data. But at the moment, what you'll do is you can measure the temperature, you can measure the pressure, and you can measure how much water vapor there is in the atmosphere, and you can put those together and you can infer something about the presence of oceans, at least on some planets. So I think that's sort of the first thing that we'll try to do. If there are more advanced ways that you can look at it, that's possible, but I'll try not to predict too much.
That's one of the fun things about following science is that they're very clever. They come up with new ways to look at things. And I mean, just look at the idea of biosignatures just over the last, 10 years, all of the different types of things you might look for that people in the 90s didn't even think about. Things like phosphine gas and things like that really wasn't really on the table. Now, do we have any hope there in detecting a biosphere? I mean, could we conceivably see some weird Earth-like planet with an Earth-like atmosphere, disequilibrium, and things like that with the telescope?
Yes, definitely some of that. I think we always want to emphasize that Webb is not going to be looking at Earth 2.0, like true Earth analogs, which means an Earth-sized planet at 1 astronomical unit from a solar-type star. That's beyond the capabilities of Webb. What it can look like is planets like the Traapist-1 system, as I mentioned before, which is possible because the Traapist-1 star is a small star, and so it means that the planets in the Goldilocks zone are orbiting closer to the star, and the size of the planet relative to the star, that ratio is closer to 1, and it's much closer to 1 than it is for an Earth-like planet around a solar-type star at 1 AU. But that said, of course, I would certainly expect, I wouldn't presume that life has to evolve on something that's exactly like the Earth. Probably it's more common in places that are not quite exactly as we're used to here. So people often talk about, for Webb, that we're looking for bioindicators, not so much signatures. The difference being that an indicator may not in itself show or demonstrate that there is life for sure on the planet, but it will provide some evidence that points in that direction. And there are indicators on the JWST ledger that we can do. The most famous one, perhaps, is a methane oxygen. It turns out, though, that Webb is pretty good at detecting methane. It's not that good at detecting oxygen. You need more of an optical or an even bigger telescope to do that. But there are other ones as well. One that's been proposed is ammonia, for example, because the formation of ammonia is similar to other kind of disequilibrium processes. Is it creates energy, but ammonia is not very long-lived in the atmosphere. And that is one we can look for as well. So I really think it's not just one thing. We'll try and look at many different things, many different lines of evidence, and try and put it all together. And over time, not instantaneously, but probably over some years of observations, and, looking at the data and then coming back and say, oh, we should do this instead. Look at we have this one bioindicator. Let's try and look at this other one, and then putting it all together. I think that's the kind of science we'll see in the context of habitability with Webb.
Now, the search for exomoons, which is sort of a hot topic now with candidates and things like that, does Webb offer an inroad there?
Probably not a whole lot. Those are really hard. If there's anything that I sort of off the top of my head can think of in that context, it's probably the formation of exomoons might be something that could be done. This is also more in my area of research, and so there in that context, we'll be looking at these are more giant planets. So young giant planets that are forming, if they're large enough, will create a circumplanetary disk around them that appears much like a protoplanetary disk around a star. And this is what we think happened in the Jupiter system, right, where we have the four Galilean moons that all orbit prograde in a plane. Those almost certainly formed in a disk around Jupiter. And so using the infrared sensitivity of Webb and the coronagraphic modes, we think we might be able to pick up some of those very young planets that are still in the process of forming their moon systems. And so that'll teach us something about moon systems, perhaps about the composition of them. But sort of direct detection of moons, I don't think, at least I haven't seen anything that suggested that we could do that.
Protoplanetary disks, and I know this is getting into what your research is. The idea of planet formation and being able to study, just how do star systems form seems to be right exactly in where James Webb can really look, infrared, because look, dust and material glows. So what do you anticipate there as far as our understanding of how planets form?
Yeah, so I think there are many different angles that Webb looks at. One of the angles that I'm most interested in is not just how planets form, but also how they get their chemical materials, what materials they form out of. And of course, that is important for the emergence of life, because habitability is not just being at the right temperature, but also having available the right chemicals. Water being the most obvious one, but there are other ones as well, like nitrogen. It's hard to get to planetary surfaces. And so Webb can really make a difference there, because the infrared, you're right that the dust glows in infrared, but in the infrared, we can also, using the infrared spectroscopy of Webb, that region contains what we call the molecular fingerprint region. And so different molecules provide different spectral signatures. And these are the very same signatures that are used in exoplanet atmosphere observations. But we can use the same ones in protoplanetary disks at a time. Before the material has been accreted into planets, we see it spread out in the disk. And we can use the spectroscopy of Webb to measure how much water is there, how much methane is there, how much ammonia is there, for example. And so we can then make an inventory of the chemistry in the places where Earth-like planets form. And then we can compare that inventory to measured compositions of exoplanet atmospheres as well. And we can sort of draw a thread between the two and really get an understanding for how that material ends up on the surfaces of the planets and how easy it is. And that will tell us something about how common planets with the right ingredients for life are.
Yeah, that's interesting, because you need quite a bit to happen to get there. And it's an open question still whether that's common, or if Earth is some sort of outlier, and something special happened, that doesn't usually occur. Now, do you expect inside those protoplanetary disks, do you expect the materials to be sort of spotty, or do you think it'll be relatively homogeneous? Meaning, will there be differences at the outer edge chemically of a disk as opposed to where, say, an Earth-like planet would form within the habitable zone?
That's a great question. I think we expect it to be a very large gradient, huge differences within the disk, and this is how things usually turn out, right? You start with not that powerful capabilities to look at these things, and you interpret them as if they're this monolith of homogenized material, and then as soon as you increase your resolution, and you can look at different regions, the inner disk, the outer disk, you start to realize that they're very different because they have very different conditions, they have very different temperatures, time scales, and so the chemistry is very different. And so we see strong signatures of that already with other observatories, and we certainly expect to see the same with Webb. And so there's going to be a lot of work interpreting what we see and modeling it. And we see similar heterogeneity, differences in different regions in our own solar system. And it's not just a sort of a subtle property of the early solar system or planetary systems. This is really something that determines the architecture of planetary systems, right? One of the most famous boundary regions in a protoplanetary disk is the ice line or the snow line. So the distance from the star at which the disk is cold enough that ice can freeze, or the water can freeze out into ice. Right? So beyond that, you have all the water as ice, and inside it you have all the water as vapor or as steam. And it makes a huge difference because water and other volatiles like that, they actually carry a lot of the mass of the dust. And so the more mass you have in dust, the easier it is for it to clump together and form planet cores. And so it's one reason we think it's a lot easier for forming planetary systems to form giant planets beyond, or at distances larger than the snow line and inside of it. And so I think we'll really learn a lot more about how that works.
Now, do you have, now I know we've been looking at infrared periodically since IRAS, maybe before. And in that time, a lot of protoplanetary disks have been noted, stars with dust disks. Do you have any really good candidates, ones that, that are sitting at the top of the list for forming planets currently, or at least from our perspective?
Yeah, absolutely. Yeah, that's actually a fair number of them. Of course, we want to try and get the ones that are the closest. The most famous one is one of the very closest ones. It's called TW Hydra. And that's certainly in the list for Webb in the first year. This is a star that is just a little bit less massive than the Sun, I think 0.7 solar masses. And it's located at a distance of only about 50 parsecs. Most other disks are about twice or three times as far away. We have beautiful radio images of it with ALMA. We have beautiful data of it that was taken with the Spitzer Space Telescope in the infrared. So we know that this disk has, for example, water in it and other molecules. And it has rings in it and has an excavated inner region where it looks like there's lots of signatures for active planet formation. There are probably already planets formed in there. And so this is a really good case study of something that one day might very well be host to a habitable system. But there are many others. I think in the first year, we'll probably be looking at close to 100 protoplanetary disks with Webb.
Now, say you get lucky and you catch two bodies in one of these disks colliding. I assume you would see a large flash in infrared, right?
Oh, yeah. Well, it depends on the size of the objects, I guess. And there has been some suggestions of this happening in the past. So, yeah, no, you're absolutely right. And you might see this very well in very young systems that still have a large population of planetesimals, so things that aren't quite planets yet, but still might be, 50 to 100 miles across. And there are enough of them that the probability of two of them colliding while we're, during Webb's lifetime, over the next few years is high enough that we might see something like that. So again, I can't predict if that's going to happen, but it's certainly a possibility. It would be very exciting.
It evokes what could be, what could happen, because something's going to happen that's unexpected and interesting, of course, over 10 years. But we don't know what it is yet. But at the same time, things like transient things like that can occur at any moment. And there you have it. It's sort of a bonus. But in addition, what the really amazing thing about Webb is that it's going to allow us to look and probe very, very close to the Big Bang and look at the earliest galaxy formation. Is there anything that you can infer about, well, I guess early galaxy formation doesn't really involve planets because I guess there isn't the materials there yet. But at what point does the universe get of sufficient age to where it can form planets?
Yeah, I guess that's one of the questions that we are really trying to ask. It happens fairly quickly. Right? That's one of the reasons that it's one of the reasons it's difficult to do this first galaxies project at all, and why we need Webb to do it. So just to take a step back there, the first galaxies of Webb. What do you mean by that? Right? We mean galaxies that are first generation. So when the Big Bang happened, the universe created hydrogen and helium and a little bit of lithium and a little bit of beryllium, not very much, but nothing else. And so the first stars that formed out of that material were similarly didn't have any heavy elements, all the things that we need for life in them, and they created those elements, as part of their life cycle. And so we've never seen a galaxy that didn't have any heavy elements in it. And that's what Webb will look for. It will look for these very first galaxies that are the first generation. So that process happens really fast. These very first stars, because they don't have any heavy elements, turns out they become huge, maybe 100 times, maybe up to 500 times the size of the sun. These are stars that we have no analog of in the local universe. We don't know exactly what they will look like. When you do the models, they turn out it's really big. And that means that the lifetime is really short. And so within just a few million years of that galaxy's lifetime, it's already enriched by heavy elements from those stars as they die in gigantic supernova explosions. And so to catch those first galaxies in that very brief moment in cosmic time when they're really pure is difficult to do. So I think it will happen pretty quickly early on that you would have galaxies that get enriched enough that you can potentially form planetary systems that could be hospitable to life.
It's amazing how it all evolves. You get your first generation of stars, giant exploding stars like that. And then as the universe ages, you get very different types of stars, the ones we're used to these days. And the same goes for planetary systems. Chemically speaking, I guess they over time get increasingly complex, right? Chemically, as far as compounds go. Yes. I mean, you have a continuous enrichment of the universe as it gets older. What we do see, though, is that there was a time in cosmic history where most stars formed and where the enrichment was the heaviest. Sort of a little bit more than halfway back in time, there was a peak in this activity. There was a lot of gas available, which is what you need for star formation. A lot of gas means a lot of new stars, a lot of new enrichment. And then most galaxies, as they evolve, they burn through this gas. And they enter more of sort of a steady state where there's not a lot of gas left. There might be there's stars in the galaxy, of course, and those stars go through their life cycle and they explode or otherwise emit some gas back into the interstellar medium that can form new generations of stars. But it happens much slower than it did in this very explosive period of cosmic evolution. So today we're in this period where most galaxies are relatively quiet and they form stars at a low rate. And so it also means that the rate of enrichment, the amount of added material you get in the Milky Way galaxy, for example, it happens fairly slowly. Now, in regards to star formation itself, stepping outside of protoplanetary disks, just with stars, what does Webb offer there? I mean, can we use this to study and probe, I don't know, nebulas and things like that where, star forming regions are, or are they simply too cold? I wonder about that too, because my understanding of these regions is that they're extremely cold. So any hope there?
Yeah, there's a very unique capability of infrared telescopes, and Webb is no exception. In our understanding of the interstellar medium and or in star-forming regions. And then once again, it's linked to the ability of infrared spectra to trace the molecular composition of matter. And so in this context, interstellar clouds, when they're cold enough, in the time just before they can form stars, it's extremely cold, right? It's just a few degrees over absolute zero. In those clouds, you have a lot of the kind of volatile molecules like water have all frozen out as ice. So these ice coatings on dust grains, on the surfaces of dust grains. And this is actually where we think you form most of the water in the universe. You form water chemically on the surfaces of dust grains, where you may have free hydrogen and free oxygen, and these land on the surfaces of dust grains. And then while they're on the surface of the grain, are able to combine into water. You don't form water in the gas phase in these very cold temperatures. And so you end up with these little snowflakes. These are not really snowflakes, they're more like smoke, but think of them as tiny snowflakes. And you can use an infrared telescope like Webb with a spectrograph on it to measure these ices. And so basically, again, get an inventory, a chemical inventory of the material that you form stars and protoplanetary disks out of before it actually happens. And so we think that process actually does have an important role to play in how planet systems start out. Once this material is incorporated into a protoplanetary disk that forms planets, it doesn't just revert back to zero. The chemical path it takes becomes different because the material you start with had a certain chemical composition of water, methane, methanol. We think we form a lot of methanol, for example, in the cold interstellar medium before the star formed. And this methanol is the first step toward forming complex organics. Right? So if you take these ices with water in it that has methanol in it, and you expose it to ultraviolet light, for example, from newly formed stars, it can catalyze a lot of complex chemical reactions, and you end up with this organic goo on the surface of these dust grains, and that can be incorporated into planets and form the basis for even more complex organic chemistry. So that's sort of the hypothesis, but following this chemical process through all these different steps really help us understand again how common this is and what really happens.
That's interesting because that's the key to understanding how organics exist in the universe. And I mean, we see them, we see tholins, all kinds of things, and as far as abiotic organic chemistry, but eventually that can turn into us if over time. Again, it's an evolutionary thing, literally speaking. What's your sense, based on the chemistry that we know so far, before we even get into Webb? Do you think that the chemistry that happens here in the solar system, not necessarily life, but just the organic chemistry, do you think that that's probably ubiquitous across the entire universe? Is there any reason to say, well, one area may be rich in organics, but another area may not? Is there any reason to say that, or is it probably just the case that the entire universe is pervaded with some forms of organic chemistry?
I mean, I think writ large, some things are common. I think it's not hard to get a complex chemistry, because we see this in our solar system and we see it in observations of star-forming regions. We see the same kind of thing. We see signatures or structures in this material, in the ices, or in the other kinds of material that we can compare to signatures we see in comets in our own solar system. And there's a lot of similarities. But this is writ very large. I think at the same time, we know when we look at ensembles of other forming planetary systems that there's a huge diversity among them. And we see when we look at exoplanets, and I think really we'll find this with Webb as well, once we start to measure the composition of many different exoplanets, that it's a zoo, that they're all going to be different. And some people have expressed worry that it's going to be really difficult to put things into classes and say, okay, you have this thing here, and there are many of them, and they all kind of act the same way. Like, what happens if you look at 100 exoplanets, and they're all different in various ways? They're all their own snowflake. I mean, how do you understand that? How do you move on from that? So I think once you get into details, I think everything will be quite different. And we see this as well in our own solar system, right? We know that our solar system was enriched by a nearby supernova. At least we're pretty sure about that, right? So it was enriched in radioactive elements. These radioactive elements made profound differences as they decayed and heated young planets in the future evolution. That may not happen everywhere, right? We know that something happened to cause this late heavy bombardment. 100 million years after the Earth was formed, there was another period of a bombardment with asteroids from the outer solar system that was induced by some stochastic process. Something happened out in the outer solar system that made this happen. That probably is not going to happen in other planetary systems, yet it had a profound effect on how the Earth evolved. So we do have this very stochastic process that can lead to all sorts of different outcomes. And so, I think it'll be the subject of the next decade or a couple of decades of exoplanet research, and it's really to try to look through all this noise and see, what is, get answers to these things, and what is common and what is different.
Yeah, it's interesting because, we have our own laboratory here. We have our solar system, and we can see things like that the late heavy bombardment, but yet what caused it, So it's sort of, you can fall into a trap and say, well, Earth is probably rare when you think through all of those things, the presence of the moon and presence of Jupiter and all these things that had to come together to get where we are. But at the same time, that may not be the only path, right? So we may see planets under completely different circumstances than Earth that arrive at something similar, right?
Absolutely. It's the anthropic principle. I don't know how philosophical you want to get, but of course, we all evolved to match the Earth, and that's only natural. And a different environment somewhere else in the universe, if there's life, it's going to evolve for sure to match that environment, even if that environment is different. And it's like, as you mentioned, exomoons, for example. I wouldn't at all be surprised if it turns out that if life, at least simple life, is common in the universe, that maybe it's most common on moons around giant planets. Who knows? There's certainly many more moons than there are terrestrial planets out there, and even in our own solar system, if you use that as a prior.
Well, that's kind of an astonishing thought if you think about it, because if this star system is anything to go by, then planets greatly outnumber stars in the universe, and moons outnumber planets, right? Or are we not quite far enough along to be able to say that?
I think we're not quite far enough along, but it reminds me of when I started out. There are these things that say, well, we don't really have enough data to tell us, but come on. When I started my career, there were no exoplanets known, and I do remember having discussions about them. It's like, come on, it's got to be planets all over the place. We just need the data to show us, and I suspect it's the same with the moons, but we'll see.
There's just no reason for them not to be out there. I do remember those days too, where we hadn't any confirmed exoplanets, but everybody was like, the universe would look very strange if these were the only planets in the whole thing.
Yeah.
So you just have to assume the Copernican principle that this is nothing special and that this stuff's everywhere. And lo and behold, that's what we found. And we keep finding more exoplanet candidates each year. And TESS, as I recall, is really starting to, add to the count. Now, closer in with Webb, we now have a new class of object to study we've only seen two so far, interstellar objects. Can Webb help us characterize something like Borisov, chemically speaking, or is it just too close?
No, absolutely. I'm actually super excited about this, because interstellar objects, it seems it's such a unique opportunity for us to get this piece of another planetary system just delivered to us. And Webb absolutely would be able to pick up one of those. And there are programs in the first year, target of opportunity programs, that if one comes through, that they have time to go and observe it. And Webb is sensitive enough that if Borisov had came back or something like that, that it would be able to measure its composition presumably reasonably well. And so I think the main challenge there is how many interstellar comets can we detect in time. So we have, for example, we have the Rubin telescope, which is a ground-based telescope, surveys the skies in 8 meters. I've been told that they would expect with, of course, there's an error bar in that, but with the rate that we think that these things go through the solar system now, they might pick up 1 or 2 a year. And if so, that would be very exciting, and the timing is very good for Webb. So at the end of Webb's mission, I certainly hope that we'll have a little sample of extrasolar comets that we can try and understand.
It's going to be interesting to see, because obviously there's a population of these things, and we can characterize that the more we see them, and take a look. And so far, I mean, Oumuamua was just weird, but Borisov wasn't. Borisov it's a comet, it's an exocomet. But it'll be interesting when we have like 20 or 30 of these objects known and studied to see what variation we see, because these things could be from the other side of the galaxy, for all we know. Their origin points could be anywhere, and they're right here, like a little laboratory passing through our solar system, ready for us to take a look at. And that I did not foresee. I didn't think that we would ever be able to do that. And now, no, we can now. So I think that's going to be a very rich area of discovery, don't you?
Oh, I know, absolutely. As I said, I mean, I'm really excited about that. I can't wait for the first one to come. I really hope that it's not gonna, as you say, can we follow it along? The JWST does have the weakness that it can't observe the entire sky at any given time because the telescope itself always has to be in the shade from the sun, so it can't point in the direction of the sun. Over the course of a year, we can observe any point in the sky. But, I can imagine that with an interstellar comet, you can get unlucky and it just does not go through a part of the sky that at the time that you needed to in order for Webb to observe it. So I hope we'll get a little lucky there. I hope we do. But yeah, it'll be exciting. What also boggles my mind is that with the rate that we think we have, the number of these things that just travel through galactic interstellar space is huge. I don't know the number off the top of my head, but I calculated it once. It's like this massive number, and there's a lot of mass in that just solid mass that is locked up in these cometary wanderers traveling for a billion years through the galaxy.
You could even apply the rogue title to them, rogue objects or rogue comets or things like that, because we do it with rogue planets. But it's interesting because that's, as you say, that is a lot of mass floating around out there that, I mean, I don't know if it's enough to be a candidate for dark matter, but but it's still, there's just a lot of stuff in the interstellar medium. But you have to also account for how big the interstellar medium really is, and it's actually, it turns out to not be that much on the whole because of the enormous distances. Now,
that's right.
Planetary science. What does Webb offer us for looking at the outer planets? I know it can't look at the sun, but it can look out. So
that's right. We can look at anything from Mars and outwards. The limitation is how quickly Webb can track something. So if something is inside the orbit of Mars, it just goes too fast. We can't follow it. But from Mars and outwards, we can, and there are programs to observe pretty much anything in the solar system, including Mars, and also including a large number of objects out in the Kuiper Belt. So these frozen worlds that are Pluto-like, that haven't been essentially touched since the formation of the solar system. So they're sort of fossils of the composition of the early solar system in a different way that comets are. And they probably trace another region of the solar protoplanetary disk. Other observatories really can't tell much about them. They can detect them, they can find them. But in order to measure the composition of them, what kind of ices they have on their surface, you need Webb to do that. And once again, it's a molecular signature of infrared spectroscopy and this amazing sensitivity of Webb that allows us to do that. So there are programs to observe, I believe, more than 50 of them just in the first year. So it will add a tremendous amount of knowledge about those objects. But also programs to look at some of the famous moons, Europa, Enceladus. Look at the composition of any kind of geysers coming off of there. Look for organics in them. Again, it's really hard to predict what we'll see, but we'll definitely look.
That would be fascinating. If you detect organics in one of the plumes from Europa or Enceladus, that's getting. We need to start sending probes out there. Although I guess we are with Europa Clipper. But,
yeah.
But I don't know if looking directly for life is really hard. You almost have to bring it back to Earth to look in the lab. But you could infer something's going on just based on the profile of chemistry coming out of the moon, right?
Yeah, you can hope, right, that they're just, again, you're absolutely right. We're not going to find life. You're not going to with Webb. Right? There's not going to be definitive proof of anything like that. But there can be some evocative evidence, right, that leads us to be able to do another experiment, right? Whether that's a probe or a bigger telescope or whatever it is. Having that kind of evidence that goes, look at this. Come on. This looks really interesting. I feel like, we ought to be able to, it's a matter of funding, right? We ought to be able to, with the right kind of data, to get the ability to build something that can do it. And I think we see signs of that as well. So I'm hopeful. The problem, of course, is that you have to be very patient. Right? So decide to build something new now. Webb took 25 years. The next one will take another, couple of decades, likely. So it's a game of patience.
Well, it's. We do live in a universe that operates on geologic time. Now, another question I have is volcanism. All right. So, if we look at the plumes at Europa, is there chemical signatures that could tell us that there are hydrothermal vents and things like that operating on the ocean floor? Or alternately, can we look at an exoplanet atmosphere and say that gas is from volcanism, sulfur dioxide or something like that? Is that within our capabilities with Webb?
Sulfur is or sulfur compounds is certainly within the infrared fingerprint region, and I'm sure people will look for that. I don't have the answer to it for Europa. That might be a hard one, but I certainly know that for exoplanets, it is certainly something to that they're looking at. And sulfur compounds is one of the indicators. Absolutely right.
It's going to be one of those things, just like the discovery of exoplanets. You can basically say we know there is volcanism going on exoplanets. It's just a natural thing to expect. But I've always been interested in how we could actually detect it. It's easy to detect with something like Io, where you can actually literally see it. But it gets a little bit harder with a place like Venus, where you can't directly see it. You can only infer it. And then doing that with an exoplanet is going to be amazing, because you could conceivably say that exoplanet 25 light years away has a volcano exploding on it right now, and from our perspective.
Yeah. Of course, it links to this Achilles heel of exoplanet spectroscopy as well, and that's haze. If you have a lot of particulates in your atmosphere, you essentially create this layer high up that you can't penetrate. It gets better once you go out into the infrared, but still, it limits your ability to measure the gases in the atmosphere. Right? That's why it's so hard to do on Venus to get through that. But it's true for exoplanets as well. So if you had a completely clear atmosphere, we could do way more. We will have these massive signals from all the different trace molecules in the atmosphere. But we think that probably you do have cloud layers, right? You do have hazes, you have all that kind of stuff in exoplanets. We see this already, and the fear is that there's so many hazes everywhere that you just end up getting flat spectra. I mean, hopefully the truth is somewhere in between, but a lot of folks are worried about that. When you get the first data back, it's like, the spectrum just going to be flat, and it's just going to tell us it's clouds.
Well, even still, though, I mean, you would be able to imagine what that planet looks like from that with haze. You could say, oh, that probably looks a lot like Venus or Titan. At the same time, though, I mean, we have this problem here on Earth. This is why we launch infrared telescopes into space, is because Earth's atmosphere is opaque, So if you had that and you were looking at Earth as an exoplanet from a distance, would you be able to characterize us? I mean, or are we too hazy?
No, Earth is actually not. I mean, you can just see, you look out the window. I'm looking at it's getting dark, but still kind of a blue sky, just a few clouds. So Earth is actually pretty good in that sense, and it gives some hope. And there has been experiments. I know that, like, for example, OSIRIS-REx, which was an asteroid probe mission, they looked back at the Earth and took up a full disk transmission spectrum in the infrared of the Earth, that showed this massive absorption feature from ozone, and you saw the carbon dioxide, right? The reason that we're worrying about global warming, water features, and so on. So we do know what the Earth's spectrum as an exoplanet looks like, So Earth is a good example that we don't have to worry as much, but still we'd like to see the data.
Well, it's coming. Won't be long. It's kind of interesting. We've been talking about all these materials, and they keep sort of coming back to the JWST. For example, the formation of a small amount of lithium during the Big Bang. Well, lithium mirrors. So it sort of has a sort of grounding in the very things that it studies, Anyway, I'm out of questions for you today, and I wish you continued good luck deploying the telescope and the getting the instrumentation all up and running and ready to go. And I look forward to first light more than anything.
Well, thank you, and thanks so much for having me. It's been a blast.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.